In this video, we'll be looking at functional groups, and what we're going to see with the new functional groups we're going to be talking about is that all of the rules and things we did with the alkanes are still going to apply. We're still going to be having prefixes for carbon chains and numbering and things of that nature. So these functional groups still employ some of the basic things we've already discussed. The next functional group we want to talk about are the alkenes. And alkenes only have carbon and hydrogen in them. What makes an alkene an alkene is that they have a carbon-carbon double bond somewhere in the molecule. So not everything is going to be a carbon-carbon single bond. We're going to see one carbon-carbon double bond somewhere in that molecule. Because we only have carbon and hydrogen, we're also expecting these alkenes to be nonpolar. And since they're nonpolar, they will not be soluble in water. The ending that we're going to use, that suffix we're going to use when we're naming alkenes, is that ene ending. So we're going to see that for our alkenes. There's going to be a couple of things that are new with alkenes and some of the other functional groups that we'll be talking about that we didn't have to worry about for our alkanes. And those are, we're going to need to number the carbon chain, not just for branches, but to describe the exact location of this carbon-carbon double bond. What we're also going to see is we're going to have multiple important features in the molecule. Like for the alkenes, we're going to have carbon-carbon double bonds, but in addition, there's also going to be branches. We need to know which is more important, and priority ends up being important. And what we're going to see for the alkenes and the other functional groups is that the functional groups are always more important than the branches when we're doing our numbering system. And we'll see these play out in some of the examples that we're going to do with our alkenes. So we're going to kind of name two alkenes on this slide. So we have the molecule that you see on the left and the molecule that you see on the right. And we're kind of going to do them in parallel. So the molecule on the left, first off, we recognize we're dealing with an alkene. How do we know we have an alkene? We only see carbon and hydrogen, and we see a carbon-carbon double bond. So that makes that an alkene. So we would use that ene ending. So we would get that into the name. Next, just like we would do for the alkanes, we want to talk about that longest continuous carbon chain. And here we would have 4 carbons in that longest continuous carbon chain. So that longest continuous carbon chain of 4, the prefix for 4 is but. So we would get that into the name. Now if we look at the molecule on the right and kind of go parallel to where we're at right now, well, we still have an alkene. We only see carbon and hydrogen, and we see a carbon-carbon double bond. Next, we're looking at how many carbons are part of that longest continuous carbon chain, and you see we have 4. Prefix for 4 is but. So here you see why we're going to have to use numbers. Right here at this stage, these two names are identical. I have butene and butene so far right now. But if you look at the structures, these are truly different molecules. These would be isomers of each other. They both have 4 carbons, 8 hydrogens, but the bond connectivity is different. They're truly different, so we need a way to distinguish one from the other. So for a lot of the functional groups, alkenes included, we're using numbers not just for branch locations. We need to describe where that interesting feature is in the molecule. Where is that functional group? And for us, the functional group for alkenes is that carbon-carbon double bond. So we're going to number the molecule. So the molecule on the left, going left to right in red, 1, 2, 3, 4. Or we could go right to left in blue, 1, 2, 3, 4. We can see that in the red numbering system, the carbon-carbon double bond is between carbon 1 and 2. In the blue numbering system, it would be between 3 and 4. So that means we have to use the red numbering system. So what we want to do is we want to describe where that carbon-carbon double bond starts at. And it starts at position 1. So we would call this 1 butene because the carbon-carbon double bond is starting on that first carbon. If we do the same process with the molecule on the right, we try numbering left to right in red. 1, 2, 3, 4. Or right to left in blue. 1, 2, 3, 4. We can see that the carbon-carbon double bond is between the second and the third carbon. And that's true both in the red numbering system and the blue numbering system. The functional group happens to be right in the middle of the molecule, so it doesn't matter which numbering system we're actually going to use here. They would both give the same result. In either one, the carbon-carbon double bond starts at the second carbon. So we would call this 2 butene because the carbon-carbon double bond starts at the second position. We now have a way of differentiating these two molecules by using that numbering. And we can see when we look at the name, we're seeing some of the same parts that we saw previously. That ending is always describing what that functional group is. The but, what's that describing? Well, that's describing how big is your carbon chain. And the new piece that we're looking at, this number, this is new. We didn't have to deal with this for the alkanes, but now we're going to have to start dealing with it. You're seeing the location of the functional group being described with numbering. We want to do another example of naming. So for this one, again, we want to recognize what type of molecule are we dealing with? What's the functional group? Well, we have just carbon and just hydrogen, but we have a carbon-carbon double bond. So being we have just carbon and hydrogen with a carbon-carbon double bond, that makes this an alkene. We would use the ENE ending for that. Then we would be looking at how many carbons are part of that longest continuous carbon chain. So 1, 2, 3, 4, 5, 6. We would have 6 carbons in that longest continuous carbon chain. So the prefix for 6 is hex. You'll notice that we also have a branch. If I circle the branch here in green, what's happening with that branch? Well, it's a single carbon branch. We recognize that, a single carbon branch, as a methyl branch. Now we need to describe locations. So in order to describe locations, just as we've done before, we need to number this carbon chain. Left to right in red, 1, 2, 3, 4, 5, 6. Or right to left in blue, 1, 2, 3, 4, 5, 6. So now we're kind of looking at what numbering system we want to use. And the numbering system we want to use is based off of the functional group. The functional group is always the most important thing in the molecule. That is what's going to dictate what numbering system we're going to use. So it doesn't matter in terms of the branch. The functional group is always more important than the branch. So what we need to look at is we're going to ignore the branch for the moment because that's not going to have a say in what numbering system we're going to look at. We need to look at the functional group, in this case the carbon-carbon double bond. That's what will tell us what numbering system we need to use. And looking at the functional group in the red numbering system left to right, it's between the second and the third carbon. In the blue numbering system right to left, it's between the fourth and the fifth carbon. Well, using the lowest possible number, we would use the red numbering system for this. That would put the functional group at position 2, so we're going to get that in there for the 2-hexene. Remember, once you choose a numbering system, you are locked into that numbering system. Because we chose red, everything else is based off of red. The blue numbering system doesn't really exist anymore. So we got locked into this red numbering system. Where is the branch located in this red numbering system? It's located at position 5. So we will have 5-methyl 2-hexene for our name. Again, we've talked about patterning a lot in the previous video. So we're seeing the same type of pattern over and over in the name. The ending is always telling you that functional group. The prefix here, the hex, what's that telling you? That's telling you what's going on with the carbon chain. How many carbons in that longest continuous carbon chain? The 2 numbers are always describing location. This number is describing the location of the functional group. The methyl, we know what that's describing. That's describing the branch size. And then the 5 out in front, remember numbers are always describing location. This is going to be the branch location. You're seeing this over and over again in all of the naming and all the organic nomenclature that we are working on. So we want to look at another example of naming alkenes. So first off, we want to recognize what functional group are we dealing with. This is going to be an alkene. We can see we only have carbon and hydrogen, and that we have a carbon-carbon double bond. So that's going to be an alkene. We can get that ENE ending in. Next, we're looking at how many carbons are part of that longest continuous carbon chain. 1, 2, 3, 4, 5, 6. So 6, the prefix we associate with 6 is hex, so we would get that in there. We do indeed have a branch. This is getting circled in green. How many carbons are part of that branch? We have 1 carbon as part of that branch. That would make this a methyl branch. So next we're looking at figuring out how to describe the locations of these various features that we see in the molecule. So again, we're going to number the carbon chain. Left to right in red, 1, 2, 3, 4, 5, 6. Or right to left in blue, 1, 2, 3, 4, 5, 6. So again, the most important part of the molecule is the functional group. So the functional group is going to decide which numbering system we're going to use potentially. But when we look at the functional group, it is right in the middle of the molecule. Regardless of whether we use the red numbering system or the blue numbering system, it would both be between the 3rd and the 4th carbon for that functional group. So being it's a tie, it's literally a tie. It doesn't matter red, doesn't matter blue right now for the functional group. When it's a tie, it's in this case that the branch can get used in terms of helping to decide the numbering system, because the numbering system, whether we go red or blue, does not affect the position of the functional group. But here we can use the branch. Well, we can see with the branch now that we're going to get a lower number if we use the blue numbering system. So we have to use the blue numbering system. So in the blue numbering system, the functional group would be between the 3rd and the 4th carbon. That would make that a 3-hexene. The branch is located on the 2nd position, so we would get 2-methyl 3-hexene. Again, it's going to be the functional group that decides the numbering system that's used, but sometimes when the functional group is right in the middle, it's going to be a tie going either way in terms of the functional group. In those situations, the branch does have a say. And only in that situation does the branch have a say, when it truly doesn't matter for the functional group. And again, you're seeing the same parts of the name, the ending for the functional group. You're seeing the carbon chain, hex. You're seeing the descriptor of the location of the functional group. You're seeing branch size. You're seeing branch location, all laid out in the same format for every single name. That's part of that patterning, recognizing what part of the name is describing what specific part of your structure. We want to do an example going the opposite way, going from name to writing out what that structure is going to be. So again, the most important parts that we want to start with are kind of the functional group and how many carbons we're dealing with in that carbon chain. We see we're going to have an alkene based upon the ending, so we're going to have a carbon-carbon double bond somewhere. And the heft is telling us how many carbons are part of that longest continuous carbon chain. So we're going to get our 7 carbons in place. So 1, 2, 3, 4, 5, 6, 7. We got our 7 carbons in place. We're going to get the functional group in place. We have a carbon-carbon double bond. Where is that carbon-carbon double bond located? That carbon-carbon double bond has to be located between the first and the second carbon. That's what the number 1 is telling us. So I'm going to go ahead and get my double bond in, and we can make that a little bit neater. We're going to get our carbon-carbon double bond in between the first and the second carbon. Now we also have a branch. Now I chose just to go left to right because that's the way we normally read and write. So we got our carbon-carbon double bond in. Now I have a branch. How big is the branch? It's an ethyl branch. So that's 2 carbons. At what position? Position 5. So position 1, 2, 3, 4, 5. We'll count over to the 5th carbon. We'll have a 2 carbon branch at that position. So at this stage right now, I have my carbon skeleton in place. I have my carbon backbone. It's at this stage, notice I haven't done anything filling in hydrogens yet. Remember, you always want to fill in hydrogens last, because if you start filling them in before any earlier, you're going to end up with the wrong number of bonds to carbon. You always set your carbon skeleton, your carbon framework first. So now how do we figure out how many hydrogens go in each position? Well, we're using that 4 bond to carbon rule. The carbon all the way on the left, how many bonds does it have? It has 2 bonds. So how many hydrogens does it need? 2 to bring up to a total of 4. The next carbon over has 3 bonds already. So that means it's going to need 1 hydrogen to get up to 4. Next carbon over has 2 bonds. That's going to require 2 hydrogens to get up to 4. Next carbon over, 2 bonds, 2 hydrogens. Next carbon over already has 3 bonds. That means it will only need a single hydrogen to get up to 4. If I look at the carbon pointing down now, 2 bonds to get up to 4 will take 2 hydrogens. Carbon all the way on the bottom only has 1 bond, so to get up to 4 bonds, I will need to add 3 hydrogens. Now back to the carbon chain, 2 bonds, 2 hydrogens. Carbon all the way at the end on the far right hand side has 1 bond, so to get up to 4 bonds, I would need 3 hydrogens. So here we would have our structure. And remember, you always want to get your carbons in place first and then go back and fill in your hydrogens at the end. Our next functional group are the alkynes. And what makes an alkyne is that, again, we only have carbon and hydrogen. But what makes an alkyne is alkynes contain a carbon-carbon triple bond. So somewhere in the molecule, you're going to end up seeing a carbon-carbon triple bond. Just like the alkanes and the alkenes, our alkynes end up being nonpolar. That means they're not going to be soluble in water. The ending that we use for alkynes is the YNE ending. Now, everything we just did previously for the alkenes still applies to the alkynes. The only difference is alkenes, carbon-carbon double bond, ENE ending, alkynes, carbon-carbon triple bond, YNE ending. All of the same general numbering, branches, prefix rules, all of that is still consistent. The only changes now you're seeing are new functional groups and new endings associated with those functional groups. We want to look at an example of naming an alkyne. So in this, first thing we want to identify is what functional group we're dealing with. Here you can see that we're dealing with an alkyne. We can recognize that this is an alkyne because we only have carbon and hydrogen, but we see a carbon-carbon triple bond in the molecule. That's what makes this an alkyne, so we're going to get the alkyne ending in there, YNE. Next, we're looking at how many carbons are part of that longest continuous carbon chain. We'd have 1, 2, 3, 4, 5. So 5 in our longest continuous carbon chain. The prefix we associate with 5 is pent. So this is a pentyne. Next, we're looking at branches. So I'm circling the branches. I have a branch here, a single carbon branch, and a branch here as well, a different single carbon branch. They're both single carbon branches, so they're both methyl branches, so I'm going to get that into our name. I have 2 of those methyl branches though. So here I'm going to use the dimethyl. Remember, when you have more than one branch of the same size, instead of saying methyl-methyl, we can kind of combine that to say dimethyl. Now, just like always, we're looking at having to describe the location for some of these key features. So when we look at location, we would need to number the carbon chain. Left to right in red, 1, 2, 3, 4, 5. Or right to left in blue, 1, 2, 3, 4, 5. Again, it's the functional group that's going to dictate which numbering system we need to use. So when we look at the functional group, that's the carbon-carbon triple bond. And we can see right away that the red numbering system is the one that we should use because that puts the functional group between the first and the second carbon. If we use the blue, that would be between the fourth and the fifth. So we would want to use the red numbering system for the lowest numbers for the functional group. So we would use a 1 here, 1 pentyne, because we want to use the lowest number. Where does the functional group start at? So now we're locked into that red numbering system. Where are the branches at? Well, I would have a branch at position 3 and a branch at position 4. So here I'd be looking at 3,4-dimethyl 1-pentyne. And again, you're seeing all these common patterned features in the name to describe a specific part of the molecule. YNE ending, that's telling us our functional group. It's an alkyne. The pent, well, how many carbons in that continuous carbon chain? The 1 is telling us the location of that functional group. The methyl, how big are the branches? The di is describing that I have 2 of those methyl branches. And then finally, the 3 and the 4, the location of those branches. You're seeing the same format, the same pattern over and over again for every single organic structure that we name. We want to make sure we're able to go in the reverse direction as well, not just looking at a structure and being able to name it, but taking the name of a structure and being able, or taking the name of a compound and then being able to write the structure from that name. So here, again, we want to look at carbon chain and functional group first. My YNE ending is telling us we have a carbon-carbon triple bond somewhere in the molecule. The hex is telling us how many carbons in that longest continuous carbon chain. So I'm going to get my 6 carbons in. 1, 2, 3, 4, 5, 6. I have my 6 carbons in place. It's telling me I have a triple bond that starts at position 3. So we count over 3 carbons. That's where we're going to start the triple bond at. So 1, 2, 3. I'm going to need a triple bond between the 3rd and the 4th carbon because it's where it starts at. The number for your alkenes and your alkynes describes where does that functional group start at, not what it ends at. I have some branches. Dimethyl means I have single carbon branches, but I have 2 of them. What position are they in? They're both on the 2nd carbon. We see that from the numbers out front. So again, we just started counting left to right. So I need 2 methyl branches on that 2nd carbon. So now what we have right now that we're looking at is we have the carbon skeleton. We have that carbon backbone. Last step, filling in the appropriate number of hydrogens. So if I look at the carbon all the way on the left, it has 1 bond. Carbon gets 4 bonds. So to make that happen, I need to put 3 hydrogens in. The next carbon over already has 4 bonds. I can't add any hydrogens to that. Every carbon we draw is going to have 4 bonds to it, so we're going to leave that alone. It can't hold any more hydrogens. If we put any hydrogens in it, we'll have more than 4 bonds, and that's not going to be okay. So now we look at the carbon above. The carbon above has 1 bond, so to get up to 4 bonds, we need 3 hydrogens. Same thing happens for the carbon below, 1 bond. We would need 3 hydrogens to get up to a total of 4. Now we're back on the carbon chain. The next carbon over already has 4 bonds. Can't handle any hydrogens, leave it alone. Next carbon over also already has 4 bonds, can't handle any more, leave it alone. Next carbon over in the chain going to the right has 2 bonds, so I would need 2 hydrogens to get my total up to 4. Then the carbon all the way on the right-hand side of the chain has 1 bond, so we would need 3 hydrogens in order to bring that total up to 4. So here we have our structure. And again, we're drawing structures the same way. We're getting our carbon chain in. We're getting the functional group. Then we're putting branches in. And then finally, at the very end, we're adding in the hydrogens. So we want to follow the same pattern for all the different examples, all the different structures that you are writing. So our next functional group that we want to talk about are the alcohols. So alcohols are our first functional group that have something besides carbon and hydrogen in them. Alcohols will contain carbon, hydrogen, and oxygen in them. And what makes an alcohol is an alcohol will contain an OH bonded to carbon. So we'll see that in all of these alcohols. Now, when you first look at an alcohol, you might be tempted because it kind of looks a little bit similar to something we talked about in the previous unit. We talked about hydroxide ion a lot in the previous unit, that hydroxide ion is strong base. That's what makes something basic. This is not a strong base. These alcohols are not bases because they're not ionic hydroxides. This molecule has no way of giving off that OH as an ion, so these are not basic at all. These alcohols do end up being polar though. So alcohols tend to be polar. Why do they end up being polar? Well, we see that oxygen. Oxygen is very electronegative. Hydrogen, not very electronegative. So we actually have a little bit of an electronegativity difference here in the molecule finally. And because of that, these molecules are polar. Now, when we compare polarity of an organic molecule to water, what we have to remember is that water is very, 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 very polar. It is one of the most extreme polar compounds we have. If something's just a slightly bit polar, it still won't dissolve in water because the difference is too great in the polarity. So there's a rule that we have for alcohols, and we'll see this rule also works for a couple other functional groups, in that alcohols with 4 or fewer total carbons are water soluble. Those with more than 5, those with 5 or more carbons are not going to be water soluble. And I have a little cartoon drawing here to kind of demonstrate that. The reason why this rule exists is because you have to think about what part of the molecule is polar, what part of the molecule is not polar. So on the left, that I kind of have boxed in red right now, I drew a cartoon drawing of a small alcohol. That squiggly line represents only a few carbon atoms. The only polar part of the molecule is the OH. That's what makes alcohols polar. The rest of the molecule, all of those carbons are not polar. So here, that OH, because it's a small molecule without too many carbons, is able to make the entire molecule polar enough to be water soluble. If you compare that to the molecule on the right that I have boxed in green, notice there I have a much bigger carbon chain represented by the wavy line. Remember, the only polar part of the molecule is that OH group. Even though that OH group is polar, it is such a small component of the overall molecule that that very long nonpolar carbon chain won't let that dissolve in water. Even though the molecule on the right is polar, it's not polar enough in order to dissolve in water. And that's where this 4 bond or 4 carbons or fewer rule comes in for alcohols, in that if you don't have that many carbons, the OH can get the whole molecule to dissolve in water. If you have a whole lot of carbons, 5 or more, even though the OH is polar, it's not enough to counteract all of those carbons with their non-polarity, and they will not be water soluble. When we're looking at alcohols, what we associate with alcohols for its ending is the anol ending. So you'll see alcohols ending in anol. So here we want to look at naming some of these alcohols. So the very top one that you see first, we're going to recognize that we're dealing with an alcohol. How do we know we're dealing with an alcohol? We see that OH bonded to that carbon. So right away we know we're dealing with an alcohol. We're going to get the anol ending in for our name. Next we would look at how many carbons in that longest continuous carbon chain. And 1, 2, 3, 4. You have to be careful counting. It's very tempting to accidentally or mistakenly count the oxygen in there. Remember, oxygen is not carbon. It's not going to count as part of that carbon chain. We have 4 carbons in that carbon chain. So the prefix for 4 is but. So we would get that in there. We do have a branch. If I circle the branch here in green, how many carbons are part of that branch? There would be 1 carbon as part of that branch. That would make this a methyl branch. Last thing we would be looking at is describing locations for the key features. So we would have to number the carbon chain left to right in red. We would have 1, 2, 3, 4, or right to left in blue. 1, 2, 3, 4. Again, the functional group is the most important part of the molecule. That's what's going to dictate which numbering system you use. Here, the OH is either on in blue position 1 or red position 4. We want to use the lowest possible number, so we would have to use the blue numbering system. That puts the alcohol at position 1, so we'd get 1 butanol in. And again, using that blue numbering system, that would put the branch at position 3. So we would have 3-methyl, 1-butanol. And again, you're going to recognize the same parts of the name that we've been seeing. That ending, that enol ending, well, ending tells you what functional group. Next, you'd have a descriptor of the carbon chain, in this case, but. Remember, following the same pattern as all of our other molecules, the location of the functional group, methyl is describing the branch size, and the 3 is describing that branch location. You see that pattern over and over and over again for all the different naming that we do. If we look at the next structure, the structure that's written in the middle, again, we're dealing with an alcohol. We know it's an alcohol because we see the OH group attached to the carbon. So we would get the alcohol ending in here, enol. Next, we would count our carbon chains. So 1, 2, 3, 4 carbons in that longest continuous carbon chain. So that would still be but. So we would get our but in there. We do have a branch. If I circle the branch in green, how many carbons are part of that branch? There's 1 carbon in that branch, so that would make that a methyl branch. And then our last step is to do our numbering so we can describe locations. Going left to right in red, 1, 2, 3, 4, or right to left in blue, 1, 2, 3, 4. Remember, it's a functional group that matters, so we're looking at the carbon that the OH is on. In the red numbering system, it's on position 2. In the blue numbering system, it's on position 3. That means we would have to use the red numbering system. So that puts the alcohol at position 2. So we would use a 2 to describe the position of the alcohol. That puts the branch at position 3. So we'd be looking at our name of 3-methyl 2-butanol. Now if we look at the structure on the bottom, we're still dealing with an alcohol. We recognize that because we see that OH attached to the carbon. So we would get our alcohol ending of enol. We'd be looking at figuring out the carbon chain. How many carbons in that longest continuous carbon chain? 1, 2, 3, 4. There are 4 carbons in that longest continuous carbon chain. Prefix for 4 is but. Next, we'd be seeing if there are any branches present, and we do have a branch circled in green. How many carbons are part of that branch? 1, so we're looking at a methyl branch again. Next, we would have to describe locations. So we'd have to number the carbon chain, left to right in red, 1, 2, 3, 4, or right to left in blue, 1, 2, 3, 4. So now we're deciding which numbering system we want to use. Again, lowest possible number for the functional group, so the OH. So we're looking at the carbon that has the OH on it. In the red numbering system, it's position 2. In the blue numbering system, it's position 3. So lowest number, we would have to use the red numbering system. That puts the alcohol, the functional group, at position 2. So we would get that in there. And the branch is also at position 2. So we would get 2-methyl 2-butanol. And again, you're still seeing the same common pattern for the different parts of our naming. There's something else we want to do with alcohols, and it's not really tied into the name, but we want to kind of take care of it at this moment because this is going to be very important when we go back and talk about alcohol reactions and reactions of alcohols in a future video. So right now we're just going to focus on classifying. So this is a classification of alcohols. It turns out there are 3 groups of alcohols, and these get classified based upon the number of carbon atoms directly bonded to the carbon that has the OH. And what we're going to find is that if there is 1 carbon directly bonded to the carbon with the OH, we call that a primary alcohol, sometimes shorthand symbolized as a 1 with a degree symbol. You have 2 carbons directly bonded to the OH, we end up with a secondary alcohol, sometimes symbolized with a 2 and the degree symbol, kind of second order. If 3 carbons are directly bonded to the OH carbon, we get what's called a tertiary alcohol that has the 3 with the degree symbol. So we're going to do some examples where we actually use this to classify alcohols. And we're going to use the same alcohols that we use in terms of naming in order to talk about how these would be classified. So the thing we want to look at when we are classifying an alcohol is we want to look at the carbon that has the OH. So I'm looking at the carbon that has the OH. In each alcohol, I'm going to box that in red. I'm finding the OH, and I'm finding which carbon has that OH attached. That's where we're focused on. Then, in order to determine what the classification is for each alcohol, whether it's primary, secondary, or tertiary, what we want to look at is how many carbons are directly attached to that carbon that we have boxed in. We box in the carbon with the OH. Now we're looking at how many carbons are directly attached to that. And in the top one, highlighting it in yellow, there's only 1 carbon directly attached to the carbon that's boxed in. It doesn't matter how many other carbons there are, there's only 1 other carbon directly attached to that carbon. So being there's only 1 other carbon directly attached to the carbon with the OH, we would call that type of alcohol a primary alcohol. Now if we look at the middle structure, again, we have boxed in the carbon with the OH, and now we're asking how many other carbons are directly attached to that carbon. I'm going to highlight them in yellow. Well, the carbon on the left is directly attached to that carbon, and the carbon on the right is directly attached to that carbon. So the boxed in carbon, the one that has the OH, we have 2 other carbons directly attached to it. That's going to make this middle alcohol a secondary alcohol because there are 2 other carbons directly attached to the carbon with the OH. So we have a secondary alcohol. Now if we look at the bottom carbon, again we have the carbon that has the OH boxed in red, and now we're looking at how many other carbons are directly attached to that carbon. So I'll highlight these in yellow. The carbon on the left is directly attached, the carbon below is directly attached, and the carbon to the right is directly attached. So being we have 3 carbons that are directly attached to that carbon with the OH, that is what makes this alcohol a tertiary alcohol. So when you are trying to classify alcohols, you're looking at the carbon that has the OH and then counting how many other carbons are directly attached to that. And this is going to be really important when we start talking about reactions in a future video, because what we're going to see coming up in the future is that primary alcohols will react differently than secondary alcohols, and those will react differently than tertiary alcohols. And that's going to be important that we're able to classify which type of alcohol we have in order to understand how it will react. We want to do an example of an alcohol going the opposite way. So starting with the name, being able to write out that structure. So for this one, we have 3-ethyl 2-hexanol. So again, what functional group are we looking at? The enol ending tells us we're dealing with an alcohol. How many carbons in that longest continuous carbon chain? There are 6. That's what the hex is telling us. So we're going to get our 6 carbons in. And again, we're going to count from left to right. Where is the functional group? Well, the functional group, the alcohol's on the second carbon. So counting from left to right, I need to put an OH on the second carbon. Now we're looking at this and we're saying, okay, next piece would be to get in any branches. I have an ethyl branch. That's a 2-carbon branch. An ethyl branch has 2 carbons in it in the third position. So in the third carbon, I need to get a 2-carbon branch in here. So I'm going to get that in. What we're looking at now is the carbon skeleton, the carbon backbone, the carbon framework. I have all the carbons connected correctly. I have the right carbon chain. I have the right functional group in the right position. I have the right size branch in the right position. Here's my carbon skeleton. Now I'm able to fill in hydrogens. So that carbon all the way on the left-hand side, that one has 1 bond. So to get up to 4, I would need 3 hydrogens. The next carbon over has 1, 2, 3 bonds to it. So that will only require 1 hydrogen. Now when you look at the oxygen, we could have pointed this out in some of the other alcohol structures that we had. Remember, oxygen only gets 2 bonds. Oxygen has its 2 bonds. That oxygen we have is bonded to the carbon and it's bonded to the hydrogen. So it has its 2 bonds. We don't need any more. We're going to leave that alone. The next carbon over in the chain has 3 bonds, so I'm going to need 1 hydrogen. Now if I'm looking at the carbons going down, 2 bonds, so 2 hydrogens. Carbon all the way at the bottom, 1 bond. To get up to 4, I will need 3 hydrogens. Now back to the carbons in the chain, 2 bonds to get up to 4, 2 hydrogens. Next carbon over, 2 bonds, need 2 hydrogens to get up to 4. And now the carbon all the way on the right has 1 bond. To get up to 4 total bonds, I would need to add 3 hydrogens. So here's our final structure for 3-ethyl 2-hexanol. The next functional group we want to look at are the thiols. And for the thiols contain carbon, hydrogen, and then sulfur. And thiols are a little bit similar to alcohols, except that instead of an OH, you have an SH. So thiols will have an SH bonded to the carbon. Thiols end up being slightly polar. They're less polar than the alcohols are because sulfur is not as electronegative as oxygen. That means they're only slightly soluble in water. The thing we want to associate with thiols is the odor from thiols. And this is that very characteristic skunk odor. That skunk odor that you associate with a skunk, that has that smell because of the thiols in that skunk spray. Now we're not going to go through naming and structure writing for thiols the same way we did for the other functional groups, but we do need to recognize this functional group because it is still important, even though we're not going to go through nomenclature for it, because we will do reactions for the thiols, and we'll have to do organic reactions for the thiols because that will be very important later on when we talk about protein structure. So right now for thiols, we just have to focus on recognizing the functional group as well as associating that very particular smell of that skunk odor as coming from thiols. Our next functional group that we want to talk about are the ethers. And ethers contain carbon, hydrogen, and oxygen. And what makes an ether is that you will have an oxygen that breaks up the carbon chain. So what you'll have is you'll have the carbon chain, but then an oxygen will disrupt that carbon chain. So you'll get this type of structure. Now, these ethers do have oxygen, so that will make them polar, but these are only slightly polar. So being they're only slightly polar and water is extremely polar, these will not be soluble in water. Now, ethers, we end up naming these a little bit differently than our previous functional groups we've talked about because there's a disruption in the carbon chain. So these work by a little bit different process. The naming, what we're going to see is you're going to see ether as a separate word when we go through and name these. So because oxygen is breaking up the carbon chain, these get named a little bit differently. And we'll do some examples of this naming. For ethers, each carbon chain coming off the oxygen is named as if it were a branch. So we're going to see those YL endings in place. We can use the prefix di if both the carbon chains end up being the same size. If the carbon chains are different size, we end up listing them in alphabetical order. So we're going to do a couple of examples that follow this ether naming. So first we want to look at the molecule on the top. The molecule on the top, again, we want to figure out which functional group we're dealing with. And what do we see when we look at the molecule on the top? We see oxygen disrupting that carbon chain. So that's what tells us we're dealing with an ether. So I'm going to get that ether ending in here. Now the way we name ethers is we look at the carbon chains that are coming off of the oxygen. On one side I have a CH3, that would be a methyl. On the other side, I have two carbons, that would be an ethyl. So I have a methyl coming off and an ethyl coming off. Which way do I have to order those? I order those alphabetically. Ethyl first, then methyl. So this will become ethyl methyl ether. And we put the ethyl first because of alphabetical order, E before the M. Notice we have a very different numbering, we have a very different naming system here compared to the other ones. You're not seeing numbers get used, and that's because these ethers get named differently because you have that disruption in the carbon chain. You're essentially just naming the things coming off the oxygen as if they were branches. Now, if we look at the structure on the bottom of the page, we would recognize this as an ether. We would recognize this as an ether because we see oxygen disrupting that carbon chain. So that's what tells us we're dealing with an ether. So we're going to get the ether ending in here. Now we just want to look at what groups are coming off of that oxygen. So on the left-hand side, CH3, CH2, CH2, that has 3 carbons. So what do we call a 3-carbon branch? Well, a 3-carbon branch would be a propyl branch. Then if we look at what's coming off the right-hand side of the oxygen, we also have a 3-carbon branch. So that would also be a propyl branch. So we have a propyl on the left and a propyl on the right. Now, instead of going propyl-propyl ether, we can condense that name a little bit, and we would actually call this dipropyl ether, saying that we have 2 propyl groups coming off of that oxygen. So again, you're not using numbers for the ethers. These have a different way of them being named. Let's look at an ether going the opposite way, starting with the name, being able to write the structure. So here we have butyl ethyl ether. Well, first off, we're dealing with an ether. So what does it mean to be an ether? Well, what it means to be an ether is that you have oxygen disrupting the carbon chain. So I'm going to get that in there right away. Then, what do the things in front tell us? Butyl and ethyl? Well, those tell us how many carbons are on each side. Butyl tells us on one side we're dealing with 4. So I'm going to get 4 carbons in on one side. It doesn't matter which side you put it on. The ethyl is telling us we have 2 carbons on the other side. So here I have my carbon skeleton, my carbon backbone, my carbon framework. I have the functional group in place. I have the rest of the carbons in place connected correctly. Last step is always filling in hydrogen. So if I look at the carbon all the way on the left, remember every carbon needs 4 bonds. Carbon on the left has 1 bond. That's going to require 3 hydrogens. Next carbon over, 2 bonds, 2 hydrogens. Next carbon over, 2 bonds, 2 hydrogens. Next carbon over, 2 bonds, 2 hydrogens. Now the oxygen. Remember, oxygen gets 2 bonds. Look at that oxygen. It already has its 2 bonds. You're not going to add any hydrogens to that. Oxygen already has its proper number of bonds, which is 2. So now we're going to go to the next carbon. The carbon to the right of the oxygen, 2 bonds, 2 hydrogens. And now the carbon all the way on the right has 1 bond. So we're going to need 3 hydrogens to bring that up to 4. So here we have the structure for butyl ethyl ether. So our next functional groups that we want to look at are aldehydes and ketones. And they're a little bit similar, so I wanted to kind of put them together to show both similarities and differences. What they have in common is both aldehydes and ketones will have the C double bond oxygen in them. That's what makes each one an aldehyde or a ketone. The difference is going to be in the location, where you find this. So let's kind of talk about our aldehydes first. So our aldehydes will have C, H, and O. Here we'll have the C double bond O at the end of the carbon chain. We compare that to what's happening with ketones on the right. Ketones will still have carbon, hydrogen, oxygen, but for a ketone, the C double bonded oxygen will be on an interior carbon. That doesn't mean it's right in the middle of the molecule. It just means it's not on one of the end carbons. So aldehydes will have this happen at an end carbon. Ketones will have this happen on an interior carbon. Both of them are polar, and they're going to follow that 4 carbon or less water solubility rule. Both aldehydes and ketones that have 4 carbons or less will be water soluble. For aldehydes, we're going to see an enol ending, and for ketones, we're going to see an enone ending. Now, aldehydes will have a little bit of a special rule. Okay? For aldehydes, the functional group will always appear on the first carbon. It's always going to happen. Functional group appears at the end of the chain. That end will always be the first carbon. Because it always happens, numbers are not used to describe the location of the functional group, because it's always 1. For ketones, though, the location of the functional group can be on any interior carbon. So you have to use numbers in order to describe the location of that functional group. Now we're going to go through and do some examples of both aldehydes and ketones. So the molecule that we're looking at here, we want to kind of look at what functional group are we dealing with. That always has to be the first thing you're looking at in a molecule. What functional group are you dealing with? Well, we see the C double bond O. Where is that C double bond O? Is it on an end carbon or is it on an interior carbon? This C double bond O is on an end carbon. So that tells us we're dealing with an aldehyde. So we're going to get the aldehyde ending in. So we're going to get the anol ending in. You have to be careful with your spelling in that, because remember, alcohols have ANOL ending. Aldehydes have ANAL endings. You want to make sure you're clear and you don't mix those up. How many carbons are part of our carbon chain? Well, 1, 2, 3, 4, 5, 6. We have 6 carbons as part of our longest continuous carbon chain. Prefix for 6 is hex. Now for our numbering system, here we can see right away, because it's an aldehyde, that tells us which end of the molecule we have to number from. Functional group's always the most important. Aldehydes will always have that functional group at the end of carbon. So we have to start there for our numbering. 1, 2, 3, 4, 5, 6. What do we have? We have a branch that we still have to describe as well. How many carbons in that branch? There's 1 carbon in that branch, so that makes this a methyl branch. Now we have to describe locations. Again, we only have one choice for numbering systems. It has to start with the carbon of the functional group. That has to be 1. Now here's where aldehydes differ a little bit. You're used to putting a number into describing that functional group. You had to do it for alcohols, you did it for alkenes, you had to do it for alkynes. Here, we're not going to put in a 1 there, because when we're dealing with an aldehyde, it's always going to be 1. That would be redundant information. We do have to base things off of the aldehyde being on the first carbon in order to describe branches, though. We can see our branch is at position 5. So this would be 5-methyl hexanal. Notice no number to describe the location of the aldehyde, because by definition, aldehydes will always be on that very first carbon. Here we want to do an aldehyde going the opposite way, 2,2-dimethyl pentanal. How do we know we're dealing with a aldehyde? Well, the ending anol tells us we're dealing with an aldehyde. The pent tells us how many carbons this aldehyde has in that longest continuous carbon chain. So here I'm going to get my 5 carbons in place. 1, 2, 3, 4, 5. This time I'm going to put the aldehyde on the left-hand side of the molecules. An aldehyde, the C double bond O has to be on an N carbon. I'm going to choose to put it on the left-hand side. So I'm going to get my C double bond O in. Now I'm looking at my branches. 2,2-dimethyl. Well, methyl is a single carbon. The di tells us we have 2 of those single carbon branches, and they're at position 2. Remember, we started left to right, so I'm going to get my methyl branches in the second position. What we're looking at right now, this is our carbon skeleton, this is our framework, this is our backbone. Our functional group is in place correctly, our carbons are in place correctly, our branches are in place in the right size and location. So we have a completed carbon skeleton. Last step is just filling in our hydrogens. The carbon all the way on the left-hand side has 3 bonds. To bring that up to 4, we would need a single hydrogen. The oxygen already has 2 bonds. Oxygen gets 2 bonds, so that oxygen's good. We don't need to add anything to that. The next carbon over in the chain already has 4 bonds. It can't handle anymore, so we can't put any hydrogens in. If we look at the carbon pointed up from the branch that has 1 bond, to bring it up to 4 bonds, we would need 3 hydrogens. Same thing would happen for the carbon pointed down, the other branch. 1 bond, so 3 hydrogens. Now we're back to the carbons in the chain. Next carbon over has 2 bonds, so to get up to 4, 2 hydrogens. Next carbon over, 2 bonds. To get up to 4 bonds, we would need 2 hydrogens. Now the carbon all the way on the right-hand side, 1 bond, To get up to 4 total bonds, we would need 3 hydrogens. So here is our structure for 2,2-dimethyl pentanal. And again, we're still getting our carbon chain and our functional group in first. Then we're dealing with branches. And lastly, we're filling in the hydrogens. Always save those hydrogens for the very end. So if we go through and name this molecule, first thing we want to figure out is what functional group do we see? Well, we see the C double bond O in there. So we see the C double bond O. Where is that C double bond O? Is it at the end, or is it in an interior carbon? This case, the C double bond O is in an interior carbon. That means we're dealing with a ketone. So I'm going to get the unknown ending in place. Next up, just like always, we're counting carbons in that longest continuous carbon chain. 1, 2, 3, 4, 5, 6, 7, 8 carbons in that longest continuous carbon chain. The prefix we associate with 8 is oct. So we can get that in there. So we're looking at octanone. We do have a branch, circling the branch here in green. How many carbons in that branch? 2 carbons in that branch. That makes this an ethyl branch. So we can get that in. Last piece is we need to describe the locations for these key features we see in the molecule. So we would number the carbon chain, left to right in red. 1, 2, 3, 4, 5, 6, 7, 8. Or right to left in blue. 1, 2, 3, 4, 5, 6, 7, 8. Remember, the most important thing is the functional group. That is the C double bond O. So we want to use that to determine which numbering system we would use. Well, in the red numbering system, that would be at position 7. In the blue numbering system, that would be at position 2. Well, that tells us we have to use the blue numbering system going right to left. So that puts the functional group at position 2. For ketones, you always have to use a number to describe where the location of that C double bond O is at, because that could have been on any one of these interior carbons. You have to be specific which one you're referring to. So using the blue numbering system, what's the position of our ethyl branch? That's at position 6. We would get 6-ethyl-2-octanone. And again, you're still seeing the same common features in the name. You're seeing the ending. We have the unknown ending. That's telling us the functional group. The oct is telling us carbons in the carbon chain. The 2 is describing the location of the functional group. Out in front, the ethyl is describing your branch size. And finally, the very front, that 6 is describing the location of that branch. Again, that same patterning of the naming happens here. Next example we want to look at is one going the opposite direction, taking the name, writing the structure from that. So what do we have? We see that unknown ending. That tells us we're dealing with a ketone. The hex tells us how many carbons in that longest continuous carbon chain. That would be 6. Let's get our 6 carbons in. 1, 2, 3, 4, 5, 6. So we get our 6 carbons in. What do we have? We have a ketone on the 3rd carbon. I'm going to start my counting left to right. So on the 3rd carbon, I need to put a C double bond O. So I get my functional group in place for my ketone. I have a branch. That's what the methyl is telling me. Where's that branch at? That branch is at position 2. So I counted left to right. So on the 2nd carbon, I need to put a methyl branch. Now I have my carbon skeleton. I have my carbon backbone in place. Now I am looking at filling in hydrogens. Carbon all the way on the left has 1 bond. That means 3 hydrogens. Next carbon over has 3 bonds, so that means 1 hydrogen. The branch carbon, the one pointed down, has 1 bond, so that means 3 carbons. The carbon with the C double bond O already has 4 bonds. It can't handle anymore. We would leave that alone. We can't add any hydrogens there. The oxygen has its 2 bonds. Oxygen only gets 2 bonds. We can't add any hydrogens there. So now we're going farther right to the carbons. 2 bonds, 2 hydrogens, 2 bonds, 2 hydrogens. All the way on the right, 1 bond. To get up to 4 bonds, we would need 3 hydrogens. So here is our final structure for 2-methyl-3-hexanone. All right, next functional group we want to look at are the carboxylic acids. And carboxylic acids have carbon, hydrogen, and oxygen in them. And what makes a carboxylic acid a carboxylic acid is the C double bond O along with an OH. It needs both of those in place. You have to be careful. This is not a combination of an aldehyde with an alcohol. It's its own thing. You want to make sure you are able to see it in its entirety and that you're not too zoomed in that you accidentally misidentify this as either an aldehyde or an alcohol. So this will always happen at the end of the chain. These are very, very polar molecules, so that means 4 carbons or less are water soluble. Just in the name, it's already telling you that this is an acid. These end up being weak acids. So remember what weak acids do. They have the ability to give off an H+. Which hydrogen can be given off as an H+? Well, it's the one that I'm pointing at in blue. That's the acidic hydrogen. That's the one that has the potential to be given off. The ending that we use for carboxylic acids is anoic, and then as a separate word, acid. Carboxylic acids have a very characteristic smell that you're familiar with. That very strong, pungent stomach acid odor, that vomit type smell that you can instantly recognize, is due to the carboxylic acids that are in your stomach in terms of those stomach acids. Carboxylic acids are going to follow a rule very similar to what we saw with the aldehydes. Because the functional group always appears on that first carbon, numbers are not used to describe the location of the functional group because it would always be 1. It's the definition of a carboxylic acid. This functional group always happens at the end of the carbon chain. That is automatically going to make it the first carbon. So putting that 1 in there just would make it redundant, so we don't end up doing that. So we want to name these carboxylic acids. First things we would recognize is what functional group are we dealing with. In this molecule, we see that C double bond O OH on the left-hand part of the molecule. It's on an end carbon. So seeing that C double bond O OH tells us we're dealing with a carboxylic acid. So we want to get the carboxylic acid ending in there. And that would be anoic, and then acid as a separate word. Next, we would count the carbons of the longest continuous carbon chain. Again, be careful. Only count the carbons. Don't count oxygens, even if they're written horizontally. So 1, 2, 3, 4, 5, 6, 7. We have 7 carbons as part of that longest continuous carbon chain. The prefix we associate with 7 is hept. So this would be a heptanoic acid. We do have a branch. I'm circling the branch here in green. It is a single carbon branch. So being it is a single carbon branch, that makes it a methyl branch. So we want to get that into the name. We would have a methyl heptanoic acid. And now we would have to describe the location of the branch. Remember, we don't need to describe the location of the functional group because that's always on position 1. but we have to use that fact in order to describe the branch location. So right away, we don't have a choice in our numbering. The carbon of the C double bond O, OH, though, that has to be the first carbon. That's our only choice. 1, 2, 3, 4, 5, 6, 7. Where is that branch at? That branch is at the second position. So here we would have 2-methyl heptanoic acid. And remember, because this functional group has to appear on the first carbon, we don't write the 1 because that would end up being redundant. So our name for this would be 2-methyl heptanoic acid. We want to do a one going the opposite way, starting with a name, being able to write a structure from that name. So here we have 3-ethyl pentanoic acid. So I want to identify the functional group. Enoic acid tells me I'm dealing with the carboxylic acid, so I'm looking for that C double bond O, OH. The pent is telling me how many carbons in that longest continuous carbon chain. So just so it doesn't matter which end you put the carboxylic acid on, I'm going to put it on the right-hand side this time. I'm going to put my C double bond O, O, H in here. How many total carbons in my carbon chain? 5. I already have 1 in place, so I need 4 more. 2, 3, 4, 5. So I have my 5 carbons in place. I have my functional group in place. I have a branch. It's an ethyl branch, so that means that branch size will be 2 carbons. It's at position 3. Remember here, I have to number from right to left because of where I put the functional group. I put the functional group on the right-hand side. That's what's going to dictate my numbering. So here, I must go right to left. 1, 2, 3 on the 3rd carbon, I will need to put my 2-carbon branch. So now I have my carbon skeleton. I have my carbon backbone. I have my functional group. I have my carbon chain. I have my branch. Now I'm just filling in hydrogens. If I look at the carbon all the way on the left, 1 bond means 3 hydrogens, get up to 4. Next carbon over, 2 bonds, 2 hydrogens. Next carbon over, 3 bonds, 1 hydrogen. Now going down for the branch, the carbon pointing down, 2 bonds, 2 hydrogens. Next carbon down, 1 bond, 3 hydrogens. Now we're back to the carbons in the chain, 2 bonds, 2 hydrogens. The carbon all the way on the end that has the C double bond O, it already has 4 bonds. It can't handle anymore. Leave it alone. Can't have any hydrogens. The oxygen with the C double bond O, that has 2 bonds. Can't handle anymore. Leave it alone. The oxygen on the right has 2 bonds. Bonded to the carbon and to the hydrogen. It has its 2 bonds. It can't handle anymore. We're not going to add any more hydrogens. Here's our final structure for 3-ethyl pentanoic acid. Our next functional group we want to talk about are the esters. And esters contain carbon, hydrogen, and oxygen. And what we're going to see for these is there's a break in that carbon chain. And what makes an ester is you're going to see this in the structure. You're going to see C double bond O, single bond O, somewhere in the middle of the carbon chain. Then on the other side, you would see more carbons, more carbons. You're seeing that C double bond O, C single bond O break up that carbon chain. So these esters are slightly polar, but not water soluble. Because of the disruption in the carbon chain, esters are named differently than some of the other organic molecules that we talked about. The ending is enoate. We talked about some of these functional groups having characteristic smells associated with them. Esters are no different, but esters tend to smell nice. They have that kind of fruity or fumy odor associated with them, generally pleasant smells coming from the ester. Esters are named from an alcohol and a carboxylic acid. That's how you would normally make an ester. So the naming gets kind of named from these pieces, and we're going to do an example of it. The alcohol piece gets named as a branch with a YL ending, and the carboxylic acid piece gets named as the main root. And we're going to do example of this so you can see how esters get named. I would say esters are the functional groups that are most difficult to name. They probably require the most attention and the most practice in order to be comfortable with them, because they're just different than some of the other naming that we've done. So here we're looking at an ester. How do we know we're dealing with an ester? We know we're dealing with an ester because we have the C double bond O, C single bond O disrupting that carbon chain. That's what tells us we're dealing with an ester. So right away we can see we're dealing with an ester. Now what I want you to do is every time you are looking at an ester, I want you to dissect the molecule. And the place you dissect the molecule at is the place between the C double bond O and the C single bond O, right where I'm drawing this hatched line. Because what that's going to do, and it's always the same place no matter how the ester is written, it's between the C double bond O and the C single bond O. That's what's going to split the ester into the two pieces, the carboxylic acid end and the alcohol end. So we are dealing with an ester, so for our name we would have a noate here as the ending. Next, we want to identify which side of the molecule is the carboxylic acid piece and which side is the alcohol piece. The side with the C double bond O, so the right hand side, the way this one's drawn, has the C double bond O. The side with the C double bond O originally came from the carboxylic acid. The side with the oxygen originally came from the alcohol. So you're going to kind of dissect the molecule and identify the two pieces, always splitting the molecule between the C double bond O and the C single bond O. Then the side with the C double bond O is the carboxylic acid side. The side with the oxygen is the alcohol side. So the carboxylic acid side gets named as part of the root. So that's what goes with the enoate. So now you're counting how many carbons on this carboxylic acid side. 1, 2, 3, 4, 5. 5, the prefix for 5 is pent. So we're going to get our pent in here for the name, pentanoate. The alcohol side gets named as if it were a branch. How many carbons on this alcohol side? I'll highlight these in green. 2 carbons on that alcohol side. Well, a 2-carbon branch is an ethyl branch. So this will be ethyl pentanoate for that name. What you're always going to see when you're dealing with these esters is you're going to have the two halves. The carboxylic acid half gets the root that goes with the ending. The alcohol side of the molecule gets named as if it were a branch out in front. So you need to practice these a little bit. These are a little bit trickier than some of the other functional groups. Your book kind of does this a very similar color coding to show you the pieces, except it uses pink for the carboxylic acid side and kind of blue for the alcohol side. But you need to kind of practice these in order to deal with esters because they're just a little bit different than some of the other functional groups. We want to do an ester going in the reverse direction, methyl propanoate. So here, because of that ending, anoate, I know right away that I am dealing with an ester. So I'm going to get that ester functionality in right at the beginning. C double bond O, C single bond O, disrupting that carbon chain. So here I have that ester functionality. Again, right away, I can do that very key piece. Okay? I can do this very, very key piece in terms of dissecting the molecule. I always want to dissect the molecule between the C double bond O and the C single bond O. This is what splits the molecule into the two sides. And now the part with the C double bond O, the left-hand side, the way I have it drawn, came from the carboxylic acid. The side with the C double bond O always originated from the carboxylic acid. The side with the alcohol, or the side with the oxygen, originated from the alcohol. So now I can kind of look at my pieces here. The carboxylic acid, that's what gets the root. That's what goes with the root, so prop. So that tells me the carboxylic acid side of the molecule has 3 carbons associated with it. Prop is that prefix for 3. So my carboxylic acid side of the molecule needs 3 carbons. You have to be careful. You don't want to draw 3 more carbons in. 3 total carbons on that side. You already have 1 carbon drawn in with the C double bond O. So I need 2 carbons. 2 additional carbons. Now I have 3 carbons on that carboxylic acid side of the molecule. For the alcohol side of the molecule, that's what you're using as that kind of branch-like prefix out in front, that methyl. What's that telling you? That means the alcohol side of the molecule has 1 total carbon. So I need to get that in there. So now I have my carbon skeleton, my carbon framework. And remember, this all involves correctly dissecting the molecule and then identifying where your pieces are. The side with the oxygen is from the alcohol. That matches up with that branch-like name out in front. The carboxylic acid side of the molecule is the side with the C double bond O. That's where your root is coming from your prop. Last step is to figure out how many hydrogens I need to place in various locations because I've already drawn the correct backbone, the correct skeleton. Carbon all the way on the left has 1 bond to bring the total up to 4. I would need 3 hydrogens. Next carbon over, 2 bonds, 2 hydrogens. Next carbon over, the one with the C double bond O, already has 4 bonds. Leave it alone. Can't handle anymore. The oxygen on top has 2 bonds. Remember, oxygen only gets 2 bonds, so it has its 2. Leave it alone. The oxygen on to the right of the carbon has 2 bonds. That's all oxygen gets is 2 bonds, so no hydrogens get added. And finally, the carbon all the way on the right has 1 bond. To bring the total up to 4, I would need 3 hydrogens. So here's my structure for methyl propanoate. Again, esters, you always want to dissect the molecule and identify the different pieces, the different halves. Our next functional group are the amines. And amines are our first molecules that have nitrogen in them. These will have carbon, hydrogen, and nitrogen. So you're going to see nitrogen somewhere in the molecule. Amines end up being weak bases. And it's the nitrogen that is the basic part of the molecule. Remember what it means to be a weak base. A weak base means you can grab H+, and it's the nitrogen that ends up grabbing that H+. Amines have a characteristic smell to them. And this time we're kind of back to the unpleasant smells, but that kind of smell of decaying flesh, that kind of rotting flesh smell, that roadkill type smell, that very specific and characteristic smell comes from the amines that are being released from that decaying flesh. Because of the nitrogen, amines end up being polar, and these will also follow the 4 carbons or less rule, being water soluble. More than 4 carbons will not be water soluble. The ending is amine as a separate word. And what we're going to see is that our amines get named in a similar way to how the ethers are named. The carbon chains that are attached to the N are named as branches in alphabetical order. So we're going to look at some examples of naming these amines. So in this slide we have 2 amines that we want to name. Let's start at the one on the top. Right away you know you're dealing with an amine because you see that nitrogen there. So we recognize we're dealing with an amine. So we're going to get that amine ending there. So we're going to get amine in. Now we're looking at just name the groups that are bonded to that nitrogen. Bonded to this nitrogen, I have a 3-carbon chain. What will we call a 3-carbon chain? We will call a 3-carbon chain prop. So we name this amine propyl amine. No numbers, very similar to what you saw with the ethers. If we look at the structure on the bottom of the page, again, we recognize we're dealing with an amine. We recognize we're dealing with an amine because we see that nitrogen there in the molecule. So we're going to get that ending in of amine. Now we want to name the branches. Name the things coming off of the nitrogen. Well, on the left-hand side, I have a 1-carbon branch. So a 1-carbon branch would be methyl. On the right-hand side, I have a 2-carbon branch. A 2-carbon branch is an ethyl branch. So remember, I need to list these alphabetically. I have methyl and I have ethyl. Which one's going to come first? The ethyl comes first. So this will be ethyl methyl amine. Why do we have it in that order? Well, it's alphabetical. The E comes before the M. So we would have ethyl methyl amine as our name for this compound. Something you want to look at for these structures, look at the nitrogen. Count the bonds that you have to that nitrogen. You're going to see each of the nitrogens that are up there have 3 bonds. Remember that usually we associate nitrogen as having 3 bonds in our organic structures. These both have those 3 bonds. We want to name a couple more amines. So the structure on the top, we're still dealing with an amine. We see the nitrogen in there. So we definitely have an amine. So I'm going to get that amine ending in. Then we're looking at naming the branches that are coming off of it. Well, on the left-hand side, what do we have? CH2, CH3, 2 carbons. That would be an ethyl branch in yellow. The right-hand side, we have 3 carbons, CH2, CH2, CH3. That would be 3 carbons. That would be a propyl branch. And then kind of down below, highlighted in orange, we have a single carbon branch. That'd be a methyl branch. So we have an ethyl branch, a propyl branch, and a methyl branch. What do we need to do? We just need to put them in alphabetical order. Well, if ethyl, methyl, and propyl, ethyl ends up coming first. So this one would be ethyl, methyl, propyl, amine. And again, we would put these in alphabetical order. E first, then M, then P, giving us ethyl, methyl, propyl, amine for that top structure. If we look at the bottom structure, again, we're dealing with an amine. So I'm going to get that amine ending in. And now we're going to look at what's happening with the carbon chains coming off that nitrogen? Well, on the left-hand side, I have a 2-carbon chain. That would be ethyl. On the right-hand side, I also have a 2-carbon chain. That would also be ethyl. So instead of saying ethyl-ethylamine, we can shorthand this. We can condense that ethyl-ethyl into diethyl. So this bottom structure will be diethylamine. Very similar to what we have seen with the ethers. For the ethers, we listed the things coming off the oxygen as branches, alphabetized them. If they were the same branch size, we could use di. Same thing is true for the amines. We alphabetize the things coming off the nitrogen. We have 2 of the same size. We can kind of condense that down by using the di. We want to be able to do one going the opposite way, starting with a name, being able to write a structure. So we have butyl ethyl amine. Well, right away, we recognize that we're dealing with an amine. So what I'm going to do right away is I'm going to get a nitrogen into the molecule. I know I'm dealing with an amine. I'm going to get that nitrogen in there. Now I'm just looking at the groups that are attached to that nitrogen. My name tells me I have butyl on one side. Well, butyl would mean 4 carbons. 1, 2, 3, 4. So I have 4 carbons on one side. On the other side, ethyl tells me I have 2 carbons. So I'm going to get my carbons in place. Here I have my carbon skeleton. I have my carbon backbone. I have my functional group in place. Now I just need to fill in hydrogens to the molecule. So we're just using that 4-bond the carbon rule. That carbon all the way on the left has 1 bond. Get up to 4, I would need 3 hydrogens. Next carbon over, 2 bonds, 2 hydrogens. Next carbon over, 2 bonds, 2 hydrogens. Next carbon over, 2 bonds. You get up to 4 2 hydrogens. Now look at the nitrogen. How many bonds does that nitrogen currently have? Right now, that nitrogen has 2 bonds. 1 to the carbon to the left and 1 to the carbon to the right. How many bonds does nitrogen need? Nitrogen needs 3 bonds. So nitrogen needs 3 bonds. It only has 2. So I need to add a hydrogen to that nitrogen. Now we continue on with the carbon to the right, 2 bonds. So I'm going to need 2 hydrogens. And the carbon on the right has 1 bond, so I'm going to need 3 hydrogens for that. So here's our structure for butyl ethyl amine. Last functional group that we want to deal with are the amides or amides. They go by both terms, either amides or amides. Amides have carbon, hydrogen, nitrogen, and oxygen in them. And what makes an amide is this functional group. C double bond O with an NH. And this is generally somewhere in the middle of the carbon chain. So you'd have more carbons out here and more carbons up here. So you get that C double bond O, single bond NH. And these amides get formed from reactions of a carboxylic acid with an amine. And we care about the amides because these are important in protein structure. When we talk about proteins later on in the last unit, amides are very important for protein structure. These end up being slightly polar, but not water soluble. We're not going to go through the formal nomenclature for the amides. So we're not going to worry about endings, how to name structures, but we do care about amides because amides we're going to need to talk about the reactions that are involved in making and breaking apart amides, and it's going to be material that comes up again when we talk about proteins. So amides are important even though we're not doing the formal nomenclature for them because we will be talking about some of the reactions that amides have. Right now, we just want to make sure we're able to recognize what the functional group of an amide really is. So for all of these functional groups that we just did in this video, it is really important that as soon as possible, you start being able to memorize what the functional group looks like and what the ending is that we use to describe that functional group for those things we did for the nomenclature. Functional groups are the most important thing in this organic chemistry unit. You cannot do anything in organic without functional groups. We saw how important it was for naming and structure writing. It's critically important for what we do next in another video in terms of dealing with reactions. So in terms of getting yourself prepared for Unit 4 on these organic compounds, everything revolves around the functional groups. Your goal is to get as good with the names and the structures of the functional groups as quickly as possible.